everyone. So this lecture is going to be about other simple harmonic oscillators. This is other than like a mass on a spring like we've been talking about for a long time. So the first thing we're going to talk about is an angular simple harmonic oscillator. And basically what's happening here is that there's a wire hanging down, and then there's some type of thing on the end of that wire that can then angularly rotate and oscillate like that. It's hard to think of an example in real life, but just think of this circular object going back and forth between this positive angular displacement and the negative angular displacement, and that reference line is our equilibrium point, okay? So this is called a torsion pendulum, and that word torsion just means twisting, because again, this thing is twisting back and forth like that. And this oscillates about the position theta is equal to 0, which is our equilibrium position, in angular simple harmonic motion. The rotating disc, or rotating the disc through the angle theta in either direction, introduces a restoring torque. So just like the restoring force that we had with the mass on the spring that goes back and forth, this is a restoring torque, because now this is angular motion here. And our restoring torque is given by torque is equal to negative kappa. So this is another Greek letter. Kappa times theta, where that kappa is the torsion constant, and this depends on the length, the diameter, and the material of that suspension wire that the thing is actually hanging from. So think of kappa kind of like a spring constant, okay? So this has to do with what our suspension wire, just like the spring constant, has to do with the actual spring that the mass is attached to. So if we want to get an equation for our period of simple harmonic motion here, we just replace our spring constant K with our kappa, because that is the angular equivalent of our spring constant K. And then we replace mass in the period equation with rotational inertia I, because that again is our angular equivalent of mass. So we end up getting this equation here. We get our period T, capital T, is equal to 2 pi times the square root of rotational inertia I over our torsion constant kappa. All right, so again, just looking at this equation here, you can see that it's the angular equivalent of our period equation, because our period equation was that m over k inside that square root. Now, another simple harmonic oscillator is the pendulum. This is much, much more common than a torsion pendulum. But the pendulum here, we have a mass m on a string. This is our most common example of a pendulum. We call that mass m a pendulum bob. So you can see that in this picture, it says this component brings the bob back to the center. So that word bob is not a name. It's just what we call the mass at the end of the string. We call it a pendulum bob. Kind of weird. But basically, we have the force of gravity pulling down on this pendulum bob, and it's the horizontal component of the force of gravity, or Fg sine theta, when we're given this theta here, which is going to be the same as this theta here. This component is the restoring force that pulls the pendulum bob back to the equilibrium position. Okay, the other one, it pulls radially, so it's not going to cause any torque on the system here. So our simple pendulum consists of a mass, which again we call a pendulum bob, suspended from one end of an unstretchable massless string of length L that is fixed at the other end. Now, the tangential component of the force of gravity, which is our Fg sine theta, produces a restoring torque about the pivot point, like I said before. Now, that restoring torque will be equal to the moment arm times the force. And this, remember, the moment arm here is our perpendicular length from the axis of rotation, which is up at the top here, to where the force is applied. So our moment arm in this case is the length of the string, and then our perpendicular force is that Fg sine theta, which is where this equation comes from right here. The reason it's negative is because, again, this is a restoring force, which means that our force is always going to be in the opposite direction of the displacement. So in this case, the angular displacement. Now, what we can do here for this equation is we know that torque is equal to rotational inertia times alpha, our angular acceleration, so I alpha. And then also we know that force of gravity is equal to mass times acceleration of gravity. So plugging those things in, we get negative L times mg sine theta equals our torque, which is I times alpha. And then what we do here is this sine theta, we call this the small angle approximation. And what we can do here is we can assume that theta is small. So we get a radian measure of that when we have a small angle, like something like 5 degrees, which I'll show you on the next slide. Our radian measure, when we have a radian measure of that, basically the sine of that radian measure of 5 degrees is basically the same thing as just the regular angle. So because of that, we can just put our small angle approximation in and say that sine theta is just equal to theta. So that becomes theta. And then if we solve for our angular acceleration, we get this equation here, our negative mgl over I, so mass times acceleration of gravity times length of the string over the rotational inertia times our theta. Okay, so we get this equation for angular acceleration of the system. Now again, this equation here, and like I said, this is called the small angle approximation. So in order to use this equation, the angle has to be small. So for example, 5 degrees is equal to 0.0873 radians, and the sine of 0.0873 radians is 0.0872. So when the angle is very small, then the sine of the angle is basically equal to the angle when we're doing this in radians. So the above equation is basically our angular equivalent to the linear equation that we use, we talked about last time, which was our acceleration is equal to the negative omega squared times our position, where this right here is our omega squared, and then this right here is whatever position we're in away from equilibrium. So this is the hallmark of simple harmonic motion, that the acceleration is proportional to our position, our displacement from equilibrium, and it's opposite the direction, which we have this negative right here. So hallmark of simple harmonic motion, we're proportional to displacement, but opposite in direction for our acceleration. And the motion of the simple pendulum swinging only through the small angle is approximately simple harmonic motion. Now, just like I said, because we have that equation for angular acceleration and that whole term in front of the theta was similar to omega squared, we can then use this in order to get an equation for our angular velocity. So we get angular velocity is equal to the square root of mgl over I. And then with this, we can then get an equation for our period as well. So again, this equation comes from relating the equation on the last slide with acceleration is equal to this negative omega squared times our position away from equilibrium. So this right here, omega squared, was that mgl over I, and then it's taking the square root, we get our angular frequency or angular velocity. And then period, we know that period is just equal to our 2 pi over that omega. So because of that, we then get an equation for period of a pendulum. We get period is equal to 2 pi times the square root of I rotational inertia over mgl. Now, if we have a simple pendulum where all the mass is concentrated at the bob, so at the very end of that string, then what we can do here is we can say that the rotational inertia I is equal to mr squared, because that's the rotational inertia of a point mass. So we plug that in for I, and then also R would be L in this case. So we would actually plug in ml squared in for this I at the top right here, and then simplify, and we get period is equal to 2 pi times the square root of L, the length of the string, divided by the acceleration of gravity, g. Now this is our most important equation for a pendulum in simple harmonic motion. This is actually on your equation sheet. Okay, so this is the last equation, I think, if I remember correctly, for simple harmonic motion on your AP Physics C equation sheet. And then last but not least, we have something called a physical pendulum. So this is something, not a pendulum bob at the end of a massless string. Here we actually have something like a pen that's swinging back and forth from the end, or any object that is swinging back and forth in periodic motion. So when we have a more complicated distribution of mass, this again was on the last slide. Our period is equal to 2 pi times the square root of rotational inertia divided by mgh. Where H here instead of L were written here, but that H is going to be the moment arm from the center of mass of the system to the pivot point. So we can kind of pretend that all the mass is concentrated at that center of mass here. So when we get this, if we're using something to measure the acceleration of gravity, and say we have something like a rod. Now, if we have a rod that is being pivoted about the end, we know that we have to use our parallel axis theorem, our parallel axis for the rotational inertia. So we get the rotational inertia about the new axis of rotation is equal to the rotational inertia about the center of mass of that system plus mh squared. And we learned this last unit. For something like a rod, we know that the rotational inertia about the center of mass is 1/12 ml squared. And then plus our mh, h will be the distance from the axis of rotation through the center of mass to the new axis of rotation, which in this case is just 1/2 of the length. And then we square that, do all the math here, you end up getting 1/3 ml squared. So what we would do here is we know that h, which is our distance from the center of mass to that axis of rotation that you saw on the last slide, and then our rotational inertia about the new axis of rotation, which is at the very end of this rod as it swings back and forth like this. We're going to insert these things into this equation like this, and then rearrange, solve for acceleration of gravity, and we get that the acceleration of gravity is equal to 8 pi squared L over 3 times the period t squared. So this is just an example of like if you're asked to measure g using a physical pendulum, they like to ask things like this, like an astronaut goes to the moon and they only have a rod to measure the acceleration of gravity, something like that. So this is just an example of how you would use that physical pendulum in order to measure g. Okay, so that is the last slide for our physical pendulum. So today we talked about torsion pendulums, simple pendulums, and physical pendulums. These are all examples of other simple harmonic oscillators other than a mass on a spring going back and forth either horizontally or vertically like we've been talking about.